Hi everyone. So today we'll be talking about different ways to process the MCMC chain in what is ultimately the final video in Monte Carlo. So MCMC chain processing. Before we talk about MCMC chain processing, there is one thing, again, that I want to emphasize, which is sort of the difference between straight up direct Monte Carlo versus building a Markov chain or Markov chain Monte Carlo. Whenever you can do direct Monte Carlo, of course you should always do direct Monte Carlo. You should not be using Markov chain Monte Carlo. The problem is that direct Monte Carlo actually requires you to be able to sort of draw samples from a posterior directly, as opposed to sort of constructing a proposal distribution and proposing samples which could be rejected and then building from that a chain. So it's much less efficient, but on the other hand, it can be used much more broadly. So just again, as a demonstration, MC versus, or I should call this MC versus MCMC, just as a reminder. So suppose that I have a two-dimensional target, which depends on two variables. And I'm not going to write down the normalization constant, but it's going to be the following distribution: -1/2, 1 minus rho squared, and then in brackets R1 minus mu1 squared divided by sigma 1 squared plus R2 minus mu2 squared sigma 2 squared minus 2 rho R1 minus mu1 R2 minus mu2 sigma 1 sigma 2 close bracket here, close bracket there, and close bracket there. So what am I showing? It's basically a two-dimensional Gaussian. I have the one dimension centered around mu1. I have another dimension centered around mu2. So in other words, the center of the Gaussian is mu1, mu2. And then the Gaussian itself is not going to be perfectly circularly sort of symmetric. It'll have some correlation, which is designated, or the strength of the correlation is more or less dictated by this dimensionless parameter rho. So in other words, it's a fancy way of saying that I have a distribution that may look something like this, right? So in general, a two-dimensional Gaussian, but with some kind of tilt. I know how to sample from this analytically. That's not the issue. But I can choose to do Monte Carlo versus Markov chain Monte Carlo. So what would Monte Carlo look like? Well, Monte Carlo would basically be sort of a direct sampling, let's say ancestral sampling of this here. So I would, in MC, perhaps I would sample R1 conditioned on R2, or let's back up. I would sample R1, and then I would sample R1 condition on R2, right? So this would be ancestral sampling. Every sample would be accepted by construction. There's no Markov chain, and I don't need to start from any initial condition. I first draw R1 directly from its distribution, and then conditioned on its realization, I then sample R2. Great. So if I were to look at versus iteration number, what my R1 might look like, it's going to be always sort of drawn from the target, and the target distribution could look something like this. And if I look at what, each one of my R1 and R2 samples look like, so if this is, this is the R1 dimension, this is the R2 dimension, this is the target distribution, then what we'll see through numerical example, and we'll also see it sort of in the collab, is that I'm constantly drawing from this target directly. So it's not as if I'm starting off from some initial condition out here, and then I have to work my way into sort of sampling this region of the target. I don't. I'm always sampling directly from the target. What about MCMC? Well, MCMC is a little bit different. If I were to do, for example, GIP sampling, which is still more efficient, I would sample R1 or generate R1 from P of R1 given R2 old, and then I would generate R2 from P of R2 given R1 new. So maybe if I were to look at this again, I think I had plotted it this way, and this again is my target distribution, then I would start from some R2, which may be way out here, and then eventually sort of make my way into this region. So whenever given the choice, you want to avoid all of these wasted Monte Carlo samples that are basically taking you from your arbitrary initial condition. It may be physically motivated, but in the end, it's not drawn from the target distribution. And then work your way to where you actually have the density or the bulk of the density of your target distribution. What is this region called? It's called burn-in. And sometimes students comically call it burnout because it really gives you burnout trying to work out of your burn-in until you are drawing samples from your target distributions. So let's talk about it. This is burn-in removal. I wish there was a magic ball, a magic trick of some kind that you could use to sort of figure out the point at which you're reaching the end of burn-in, but unfortunately there isn't. So the problem is that, if you're looking at your sample versus your iteration number, maybe you might start from a sample here because you believe the density somehow lies in positive regions, and then eventually kind of work your way down here, and maybe here it kind of is roughly stable. So the idea is you would basically say, well, it looks like this region from here to here, roughly speaking, is not being drawn from the posterior because it looks like at the point at which you're sampling from here, you are mostly, or at the point at which you've reached sort of this region, you are roughly constant. So the idea is basically to take all of this data, or all of these samples, I should say, and then essentially exclude them from your analysis. So at the point at which you are sort of drawing samples, your R, 1 to J, you can choose to do some R, let's call it a J minimum, all the way to J, where 1 to J minimum, you've considered burn-in. And that burn-in, or those burn-in samples, can be removed. The question is, how do you go about determining when the end of burn-in has been reached? Typically speaking, you know where you started from. I mean, you know your initial condition. You know, roughly speaking, how things are tending, or where the bias is coming from, and you can look eventually where you have started losing this bias. There is, like I said, no firm trick. Now, in principle, if we knew when burn-in ended, and if we knew where the posterior density was, then chances are this would kind of be a solved problem, and we wouldn't be doing Monte Carlo to start off with. There's something else which is a little bit difficult with MCMC, and in fact, burn-in is the easy thing, but it's the notion of correlated samples. So take, for example, the fact that you can have an R1 and R2. You start, your initial condition is here. And you draw a sample and you move here. Then you draw another sample and you move here. You draw another sample and you move here. You draw another sample, you move there, and so on and so forth. Now eventually you start doing this more and more. You may start converging to this region, and this may be where your posterior is. So, or the bulk of the density, I should say, of your target is. sorry for using the word posterior all the time. We always do Bayesian applications in the textbook. The question then becomes, how independent are these samples really? Are they all useful? Well, I started here, and by the time I've hit my 3rd iteration, I'm still pretty close to where I started. So all these samples are pretty correlated numerically. They're not that different. And sure, if I move maybe 200 samples down, then these samples here are quite different from these samples here. But individually, if I were to zoom in, what I find is that these individual samples are all pretty correlated to one another. So it's almost as if I can take my data and break it up into sort of decorrelated chunks, because moving maybe 3 steps ahead or 5 steps ahead doesn't tell me much, but moving 200 steps ahead does. It's a very different sample. So maybe I can sort of reduce all of these data to the first point, and then move up 20 points and take the first one and call it a different decorrelated sample from 20 points ago. And then maybe I can look at my next series and call the next one 20 samples later, the next independent data point, and so forth. So the question is, how do I determine how quickly these data points decorrelate in a way? Right? So rather than to sort of consider every single data point, because all these data points are extremely related to one another, it may only be useful to consider sort of a thinned chain. And the question really becomes, how do I determine this thin chain? So we go basically from a R1 to J to a R, let's call it J1, to a R of J, let's call it RJ2, RJ3, and so on and so forth. And J1 or J2 minus J1 could be something like 100 data points, right? So you're only keeping, we have to again calculate what this is exactly going to be, but we're only keeping every 100th data point to make sure that all of our samples are sufficiently decorrelated. And when we have to compute quantities downstream, we use the thin chain, which is every 100th sample, let's say, as opposed to every single sample. So the question is, how do we determine how much thinning we have to do? Is it going to be every 5 data points? Is it going to be every 10 data points? It's not so clear. So let's go ahead and calculate what's sometimes called the autocorrelation. Let me go ahead and write the expression, and then let's explain it. This is the autocorrelation for the dth data point. So we start with some j min, j minus j min, plus 1 minus d, r of j minus r bar, which we'll define in a second, r of j plus d, minus r bar, divided by j min, j minus j min, plus 1, rj minus r bar squared. R bar equals 1 over j minus j min plus 1 j rj. So I've just defined r bar. R bar is simply the average from some j min to some big J of my data. What is rho d? Rho d, so I should say this is a definition, and this here is a division between numerator and denominator. So what is rho d? For those who've heard about it, again, it's plain old autocorrelation function. So you're taking rj and you're subtracting from rj the mean over this region, and you're comparing the difference of rj from its mean to rj plus d minus its mean. And then because you want rho of d to be somewhere between minus 1 and 1, then you can guarantee that by dividing the whole thing by rj minus its mean squared, over this region. So in other words, the variance of Rj over this region, and in the denominator, and in the numerator, the difference between Rj and the mean, and Rj plus d and the mean. Now, if Rj is very similar to the mean, and similarly Rj plus d is also very similar to the mean, and they're not really changing, then the autocorrelation should be 0. On the other hand, if Rj is very different from the mean, and Rj plus 1 is very different from the mean in the same direction, so they're both twice the size of the mean, then rho d is going to be a large number. Now again, it's going to be normalized, so the maximum value will probably be 1. So let's go ahead and plot what my rho d may look like in this circumstance as a function of d. Now, initially, when d is equal to 0, or when d is equal to 0, or when d is small, the autocorrelation should be very high. So in other words, you're multiplying two things together, the autocorrelation, two things which are pretty similar to one another, the autocorrelation will be a large number. Now, eventually, as the lag increases, in other words, as you're considering a data point here, another data point which is maybe, or another sample, I should say, which is 100 samples later, those may be very decorrelated. So eventually the autocorrelation function, it can dip negative, but maybe it might eventually go back to 0. The point at which the autocorrelation has more or less stabilized at 0, so let's plot it this way. This sort of tells you what your J-min should be. In other words, what the size of your thinning should be, the distance between your samples in your thin chain should be. Anything much less than this basically tells you that your samples are very autocorrelated. So you're going to say, well, I've done all this work, and now what I'm going to do is I'm going to take my samples and throw, let's say, 99 out of 100 in the garbage. Well, yes, ideally, you not only want to use thinning of chains in order to be able to sort of consider decorrelated samples, but you also want to use it to diagnose proposal distributions. So if your proposal distributions are giving rise to a row of D which is doing this versus a row of D which does this, then you clearly want to go with this proposal distribution versus that proposal distribution. So looking at sample autocorrelation is also a very important tool towards diagnosing helpful versus unhelpful chains. So a chain that decorrelates very, very slowly is said to have poor mixing. And similarly, a chain which decorrelates very quickly naturally is said to have good mixing or good mixing properties. Right? In other words, your samples are very decorrelated. And that sort of summarizes many of the tricks that we have available in order to be able to sort of clean up our Markov chain Monte Carlo samples, removing burn-in, making sure proposal distributions are okay, thinning our samples, and so forth. The subsequent portions of the textbook sort of delve into, or of this chapter, delve into some details on some advanced sampling techniques which you may be interested in, including Hamiltonian Monte Carlo samplers. But for now, this sort of concludes our introduction of Monte Carlo methods, and in particular Metropolis Hastings, Gibbs, and some diagnostic tools. Thank you. I messed up. I said something wrong through this, and then I think the first half of this video is okay. The second half is not okay.
Okay.
What my error is. I can tell you roughly where it is if we pause it.
Well, we're gonna do the same process we've been doing, right? You're gonna review it and then tell me what to cut out.
I can. So then I would redo. So then let me redo the second half of this video.
Okay.
So I don't know what we want to call it.
Well, you've been going back in and telling me, hey, this part to this part.
Yeah.
I think if we do the same thing for this one, it'll work, right? So
yeah.
You tell me, I don't know, it was like 10 minutes ago or something. Say, hey, 10 minute, 30 cut, and then start again here at 22 minutes.
Okay. Yeah. Let me keep. Yeah. Okay. Now that we've just talked about burn-in removal, what we next need to talk about is sort of how to deal with autocorrelated samples. So just to be clear, in burn-in, we start from somewhere here, and eventually we may start drawing samples from our target, and this entire region here from 0 to J-min or 1 to J-min, depending on how you define your initial your first sample, is the burn-in and is removed. But then there is another issue that we oftentimes have to deal with, and it's correlated samples. And we'll talk about this for a second. Suppose I start drawing samples, and my samples look something like this, and eventually I start drawing samples from what is the mode of the target. This is my initial condition. This is my first sample, second sample, third sample, and so forth. If I look, or if I zoom into this region here, what I notice immediately is that the initial condition versus the fourth sample are actually very closely related. They're very similar. In other words, we would call this region sort of very correlated with itself. But by the time I move maybe 200 samples later, somewhere here, what I find is that this sample and that sample are actually quite different. Although if I zoom into this region here, I also find that neighboring samples are very highly correlated with one another. So what we do is we often talk about thinned chains, where we have different regions, and we basically take one sample from each one of those regions, because the other samples in those regions are really not telling us much about much different from the sample we selected from that region, just because they're so similar. So we go from an R, 1 to J, to something that we call a thin chain, which is, for example, let's call it RJ1, which goes to ... R J I minus 1 to R J I to R J I plus 1, and so on and so forth. So we don't keep every single sample, we keep every 100th sample, let's say. So I guess a couple of questions arise. Is it 100 samples? Is it 20 samples? Like, how many should I eliminate from my chain? So let's talk about autocorrelation functions for just a second. And let's go ahead and write down its definition. And see what we have. So we start from some j is equal to j-min. J-min is the region that starts after the end of burn-in. And we go all the way up to j minus j-min plus 1 minus d. Let me go ahead and write it out. and this here is divided by the following, and R bar here is equal to 1 over j minus j min plus 1 sum over j from j min j to rj. So what is rho d? What is the autocorrelation function? So first off, it takes rj and it subtracts or considers the difference between rj and the mean over this interval. The mean, again, r bar, is simply the average of rj from immediately after burn-in all the way to the last sample. So this considers sort of the deviation of rj from its mean, and this considers the deviation of rj plus 1 from its mean. Now, when d is equal to 0, in other words, there is no difference between the two, then we can consider sort of the numerator and the denominator and find that rho d is equal to 1. Now, as d starts growing, in other words, as d starts becoming 1, 2, 3, 10, 20, and so forth, then what we find is that rj and rj plus d, obviously a subsequent sample, are going to be different. And how they differ from the mean will also differ. And so therefore rho of d will be different, and on average it'll sort of decrease. It'll start decreasing and potentially go to 0 as these samples become increasingly decorrelated. So if we plot rho d versus d, well, we might find when d is 0, a larger value for rho d, as we mentioned, or 1, and then eventually as d starts increasing, then our samples start becoming more dissimilar. Rho d may actually go negative, and then it may come back and then eventually plateau or converge out to 0. This entire region here is where the samples are correlated. The samples are positively correlated here. The samples are negatively correlated here. By the time I make it out here, the samples are pretty decorrelated from one another. So maybe this distance here is 100 data points, right? Or maybe it's 20, or maybe it's 5. Either way, this tells you basically how many samples you should eliminate or decimate from your chain in order to have completely decorrelated samples. So if it's 100 data points, you may want to consider the first data point, the 101st data point, and so on and so forth. But you eliminate everything else sort of in between, from data point 2 to data point 100, because they are just too correlated with each other. Now, you may ask the question, all this is great, but I've done all this work to be able to collect samples from my chain. Do I really need to take all this work and throw it in the garbage? Well, there's many other reasons that looking at the correlation between samples it's useful. It's not just to take sort of your samples and to throw them in the garbage afterwards, but it's also to very rapidly diagnose proposal distributions. Suppose you have a proposal distribution or a proposal distribution, your Metropolis Hastings, where you find that your correlation between samples is doing something like this. So, is doing something like this. So there is a decrease, but the decrease in the autocorrelation, but it is taking an extremely long time for your samples to become decorrelated. As opposed to another proposal distribution, sort of an extreme case, where your autocorrelation function can decay to 0 very quickly. So this would be sort of an indicative, or it would be indicative of a bad proposal distribution. It's also called very bad mixing of your MCMC chain, or very highly correlated samples all of which are bad things. This is the exact opposite. It is a good proposal distribution because your samples are quite decorrelated. It is very good mixing. Again, it's another synonym for saying that your samples are decorrelated. And yes, and it is highly decorrelated. The problem, of course, is that, such proposal distributions are typically, proposal distributions that take very large moves, that give very decorrelated samples, typically have very small acceptance ratios. So you have to be a little bit careful with that. Something like this, which is highly correlated, is much more likely to have acceptance ratios approaching 1/2, for example, simply because you're just barely tweaking your position. But the problem in doing so, of course, is that you're far too conservative and your samples are all very correlated. So, to sum up this Monte Carlo sample chapter, we've discussed, Metropolis-Hastings methods. We've discussed Gibbs sampling. We've discussed a couple of diagnostics. Later on in the chapter, we discussed some advanced Monte Carlo techniques, if you're interested in looking at them, including Hamiltonian Monte Carlo. But for now, that sort of summarizes, chapter 1 to 5 really summarize kind of the language and the basic tools. And by the time we make it to chapter 6 and onward, I should say, those really are sort of applications or important applications of many of the basic ideas that we've talked about. And a very important application we will turn to is the question of regression, starting from plain old simple y is equal to mx plus b linear regression. Thank you.